this chapter, we will be looking at concepts in probability. In this lesson, we will be discussing independent and dependent events.
So in a previous lesson, when we talked about mutually exclusive and non-mutually exclusive events, we were really talking about or events, where this event could happen or this event could happen, and kind of the consequences of this. When we start talking about independent and dependent events, this is now the and scenario. We're looking at this event happening and this event happening, okay? And so now we've got two definitions here. We've got independent events here, and this occurs when two events happen where the first event changes essentially the sample space, has no effect. I'm jumping ahead of myself here. Independent events occur when the first event has no impact on the sample space for the second event. In other words, the probability for the second event is unaffected by the fact that the first event occurred. Now, this is just kind of, at this point, just a nice way of thinking about this, okay? So for example, if we're talking about cards, if you've got a deck of 52 cards there and you say, what's the probability of drawing, let's say, a heart? That's going to be 13 out of 52. If you plug that card back into the deck and shuffle it up, for the next card, the probability of getting a heart is again 13 out of 52 because the first event didn't change anything. It went right back to where it was here. Now, the formula for independent events is that the probability of A and B, and we might want to think of it as the probability of A and B, okay, intersection, is going to be the probability of A multiplied by the probability of B. Okay? So we just multiply the two together. If that's the result for A and B, that's independent events. Or if you know the events are independent, that's how you get the probability of A and B. Now, dependent events, this is actually what I was starting to say a little while ago here. Two events are dependent, okay, if the first event changes the sample space for the second event, or changes the probability, it has some impact on the probability that the second event occurs. Okay? So the probability of event B depends on whether or not event A has occurred, and vice versa here, okay? So it's like taking a deck of cards again, and let's say the probability, again, of drawing that card and getting a, let's say, a heart is 13 out of 52. If you put that card aside and say, now what's the probability that the next card is a heart? Well, assuming success there, and by the way, we always assume success. Okay? We always assume success for the first event. Always. Always, you must. This is one of the things that threw me off when I was learning this material when I was in your position here, is that I always thought, well, wait, what happens if that first event doesn't happen, and blah, blah, blah. You always assume success in the first event. So let's say you've got that deck of cards, and we're looking for the probability that this card here is a heart. We flip it over. Oh, look at that. We got a heart. Now, the probability was 13 out of 52. You put it aside. What's the probability that this next card is also a heart? Well, there are 12 cards left that are hearts out of 51 cards that are left in this group here. So the probability that the second event is also a heart has changed, okay? And so these are dependent events here. The way we mark that is we use this notation here. The probability of A and B is the probability of A multiplied by the probability that B occurs given that A has occurred. Now this is kind of a weird way to think about it here, okay? This little line here tells us that what's happened here is that B depends on A. So assuming A has occurred, it's a change the probability for B. Now I got to deal with the new probability that B has occurred. But then I still multiply them together. This little bit right here means the probability of A given that B has already occurred. Okay? Now, let's take a look at some examples so that you can see how this works.
Classify each of the following events as independent or dependent.
Okay, so here we go. So tossing a head and rolling a 6, would that be independent or dependent? Well, tossing a coin and rolling a die here, they're unrelated here. The one is not going to affect the other, so we would call those independent here. Drawing a face card and returning it to the deck, and there's the key point here, and then drawing another face card, well, those will be independent because the sample space for the first event starts at 52 cards. But when you put that card back that you chose, the sample space goes back to 52. So it's the same thing. Choosing a king, not replacing it, and then choosing another king. Okay? Choosing a king, not replacing it, and then choosing another king. Okay? So not putting it back in that deck. So choosing a king here, the sample space for that particular event is going to be 52 because there's 52 cards in the deck. And if you don't put it back, then you're left with 51. So that first event did affect the sample space for the second event, so those are dependent. Okay, a spinner with 5 equal sections colored, red, blue, green, and yellow, and white, is spun twice in a row. Okay, the first event is spinning red, and the second event is also spinning red. So the spinner with 5 equal sections, okay, you spin it twice in a row, but you know what? That second time you spin it isn't going to be affected by the first time. You still have the same number of choices there, so these are going to be independent of each other. Okay? Couple more. 2 marbles are drawn without replacement, there it is, from a bag containing 7 red and 3 blue marbles. The first event is drawing a red marble, the second is drawing a blue marble. Okay, but if you don't put that first marble back in, then the sample space has changed, and so these would be dependent events, because the second event, the probability has been influenced by that first one. And now a coin is tossed and a standard die is rolled. The first event is tossing tails and the second event is rolling a 3 on the die. And again, those are independent of each other because tossing a coin and rolling a die, the 2 events don't change or have any impact on the sample space of the other. So they're independent.
A card is drawn from a deck of 52 playing cards, and the card is replaced. The deck is shuffled again, and a second card is drawn. Determine the probability that both cards are face cards.
Okay, so in order to get this question, to get the answer to this question, we've got to realize that these are independent events, because as soon as you put that card back in, okay, you replace that card, you've returned the sample space to where it was supposed to be. Okay, and so the probability for the second event, the sample space is returned, so it's not affected by that first one. Now, the probability of getting a face card is 12 out of 52 on that first event. The probability of getting a face card on the second event, because we put the card back, is again 12 out of 52. There are 12 face cards in the deck and 52 cards in the deck here total. Now, when you multiply those together, you will get 0.533. So my answer here is C.
We'll use the following information for the next 3 questions. Ronnie is going on a cruise. The brochure says that the probability of seeing a whale is 9/10, and the probability of seeing a seal is 3/5. What is the probability that Ronnie will see a whale and a seal?
Okay, so now we have to identify whether or not these are independent or dependent events, seeing the whale and the seal. Now, I don't know, but I suspect, based on the way this question is worded, that those are independent events. Okay, so the probability of seeing a whale and a seal is very likely going to be the probability of the whale multiplied by the probability of seeing a seal here. Okay, so what we've got here is we've got, 3/5 times 9/10 here. And if you multiply those together, okay, the 3/5 and the 9/10, you get 0.54. So that would be the probability that you see a whale and a seal. But again, you got to assume in this case that those are independent events.
What is the probability that Ronnie will not see either?
Okay, so now to interpret this thing, I guess symbolically, you might want to think of it like this. This is the probability that he won't see a whale and he won't see a seal. Now again, we assumed that seeing them was, they were independent events, so I'm going to assume that not seeing them is also independent, are also not independent. Are also independent events. Wow, that took me a while to get that out. So that means I'm just going to multiply the 2 probabilities, the probability of not seeing a whale by the probability of not seeing a seal. Now, the probability of seeing a whale was 9/10, so the probability of not seeing a whale would be 1/10. It'll be its complement, okay? The probability of seeing a seal is going to be 3/5, so the probability of not seeing a seal would be 2/5, okay? And when you multiply those together, you're going to get essentially 1 out of 25 there, okay? And that amounts to a 0.04.
What is the probability that Ronnie will only see one of these sightings?
Okay, now, this one's a little bit more interesting. Okay, what's the probability he's only going to see one of these? Okay, now, it could be the whale or the seal. That or, when we describe that, is going to imply addition here. So this is the probability that Ronnie sees, let's say, a whale and not a seal, or he doesn't see the whale and he sees a seal. Okay, so now we've got this addition here. This is going to be the probability that he sees a whale. Now, we are going to treat these as, well, sorry, they are mutually exclusive events. It's not possible that this happens at the same time that this happens. You can't see a whale and not a seal while at the same time not seeing a whale. So these are independent events, sorry, mutually exclusive events. So we're going to add together these two probabilities. So the probability of seeing a whale was 9/10. The probability of not seeing a seal was 2/5. Plus the probability of not seeing a whale was 1/10, and the probability of seeing a seal was 3/5. Okay, so it either happens yes I do and no I don't, or no I don't and yes I do. And when you multiply that all together, you get 0.42 C.
A cookie jar contains 10 chocolate and 8 vanilla cookies. If the first cookie drawn is replaced, find the probability of the following.
Okay, so here we go. So now the key to this one here is, again, that first cookie is replaced. I don't know why you put the cookie back. Just eat the cookie. Anyway, it's not even sanitary, but let's assume that happened. You know, little kid reaches in, grabs it, drops the cookie back in, didn't want the vanilla. So what's the probability of getting a vanilla and a chocolate? Now in that order, right? So this is going to be the probability of getting the vanilla multiplied by the probability of getting a chocolate. Now these are going to be independent events because the sample space is returned to the way it's supposed to be. This is going to be 8 out of 18 multiplied by 10 out of 18. Okay? So what do we got there? That's going to be 80 divided by 18 squared. And so we're looking at approximately, what is that, 0.25 when you round that. Okay, so that's the probability of getting a vanilla cookie, but dropping it back in, and then getting a chocolate cookie. Over here, what's the probability of getting 2 chocolate cookies? So that's going to be chocolate and chocolate. Okay, well that's going to be the probability of getting a chocolate multiplied by the probability of getting a chocolate, because again, these are going to be independent events. Now, the probability of getting a chocolate was 10 out of 18, and then the probability of getting that second one as a chocolate is 10 out of 18. So that is going to be 10 times 10 divided by 18 times 18, and approximately to the nearest hundredth there, we're going to get 0.31. Okay? Now let's look at this next one here. That's the probability of getting a vanilla, then drawing a chocolate cookie if the first cookie drawn is eaten. Okay, there you go. Now that makes more sense here. So this is going to be the probability of getting a vanilla and a chocolate. Okay, but in this case here, this is the probability of getting a vanilla, but now the probability has changed. This is now the probability of getting a chocolate, given that that vanilla has been removed. This is now a dependent scenario here. Okay, because eating that vanilla cookie has changed the probability that you're going to get a chocolate. So the probability of getting a vanilla here is 8 out of 18. The probability of getting a chocolate is going to be 10, because there are still, now remember, we in these situations here, you always assume success. Okay, don't look at this and think, well, what if I didn't get a chocolate in the first step? No, 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 no. When you discuss probabilities like this, you're always assuming success. You're looking for what the probability of the successful event is. Don't worry about anything else here. So we're going to assume that, yeah, you reached in, you grabbed a vanilla. Now, I've still got 10 chocolate, but now there's only 17 cookies in there to choose from. Okay? So now this is going to be 8 times 10 divided by 18 times 17 when you multiply that across. And in this case, our probability is going to be approximately 0.26.
Determine the conditional probability for each of the following.
Okay, so in this case here, we're dealing with something that's obviously got some dependence here, okay? So we're going to determine the conditional probability for each of the following. Now, what we mean by conditional probability is this little bit right here. Okay, so I'm going to pull this out of the way. So, and by conditional probability, what we're referring to here is that we're looking for the probability that B happens given the condition that A has already occurred. Now, think back to dependence. The probability that A and B occur is the probability that A occurs multiplied by the probability that B occurs given that A has already occurred. So this is the part that we're looking for. So I know that this is going to be 0.725 is going to equal 0.78 multiplied by the probability that B occurs given that A has already occurred. Now, to get this part by itself, I just have to divide. So that's going to be the probability of B given A is 0.725 divided by 0.78. And I'm going to go to my calculator. 0.725 divided by 0.78. And the answer is 0.93. Okay, or there's a 93% chance that that's going to occur. Now let's take a quick look at this one. Given the probability that being blonde and tall is 0.5, and the probability of being blonde was that given that you're tall, that's kind of weird there, it's 0.68, find the probability of being blonde. Okay, so the probability of, let's say, blonde and tall, it's the probability of being blonde multiplied by the probability of being blonde given that you're tall. So based on what I'm seeing here, this is going to be 0.5. We know that this is going to be 0.68. We were told that. So now to get the probability of being blonde, I just got to divide here. So the probability of being blonde in this case right here is going to be 0.5 divided by 0.68. And I just go to my calculator. And this will be to the nearest hundredth here, 0.74. 74% chance, okay, that you would be blonde in this circumstance there.
Events A and B are independent. The probability of A is 3/8 and the probability of B is 5/8. Calculate the following.
Okay, now with the assumption here that these are independent, if we want to figure out the probability of A and B, that's just the probability of A multiplied by the probability of B. And in this case, we're given both of those. That's 3/8 multiplied by 5/8. So just multiply across the top. It's going to be 15 over 64. There are no common factors between 3 and 8 or 5 and 8, so that's as simple as that's going to get. Okay? Now, here, we want to figure out the probability of A and not B. Well, again, because we already assume that the events A and B are independent, we can assume that the negation and the event will also be independent. Okay, so now the probability that A occurs is 3/8. The probability that B does not occur, well, okay, the probability that it does occur is 5/8, so the probability that it doesn't occur would be 3/8. There are 5 successful events, and so if there's 8 total events, there must be 3 unsuccessful events. And so now multiplying that across, 9 out of 64. And again, that's as simple as it will get because there's no common factors between 3 and 8. Over here, what's the probability that not A and not B occur? And again, because we know independence between A and B, we can assume independence between not A and not B. And so the probability that A doesn't occur will be 5/8 because the probability that it does occur is 3/8. And then just the opposite, because the probability of B occurring was 5/8, the probability that it doesn't occur is 3/8. So this is actually going right back to that first question here. And again, we get 15 out of 64, just like we did with that first one over here. Okay, because it turns out these two are actually the complements of each other. Kind of neat when that sort of thing happens.
2 cards are drawn from a standard deck of 52 cards. Determine the probability of the following events with replacement and without replacement.
Okay, so we're going to look at the same events here, but with two different scenarios here really being played out. So we're going to grab two cards from a standard deck of 52. Okay, and we're going to figure out these probabilities here. What are the probability that both cards are red with replacement? So that's the probability of getting a red and a red. Okay, red on card 1 and a red on card 2. If you put the card back, then they're independent. So this is going to be the probability of getting a red multiplied by the probability of getting that second one red. Now, the first one being red is going to be, what? There's 26 red cards out of 52. If you put the card back, you're going to get 26 out of 52 for that second card as well. Okay. Now, granted, this is going to end up being a really large numbers here, but I can simplify first. That's going to be 1/2 times 1/2, or ultimately 1/4. That's the probability that they're both red if you're replacing the card. Now, if you're not replacing the card, these become dependent events. So the probability that the first card is red and the probability that the second card is red will be the probability that the first card is red multiplied by the probability that the second card is red given that the first card was red. So the probability that the first card is red is 26 out of 52. Now, if you don't put that card back, okay, if you don't put that card back, then what we've got here is a dependent scenario where we've changed the sample space. There are now only 51 cards, and there are only 25 red cards to choose from. We don't have 26 anymore. Okay, so now we just go to our calculators here, although I suspect that this won't simplify here. And in fact, it really doesn't here. This is going to end up being, this simplifies down to 1/2, I should say. And then 1/2 times 25 over 51 is just going to be 25 over 102. So there's the probability without replacement. Now let's look here. What's the probability that the first card is a king and the second card is a 5? Okay, with replacement. Well, that's going to be the probability that the first card is a king multiplied by the probability that the second card is a 5. Again, with replacement, putting the card back, these are independent events. Okay, there are 4 kings out of 52 cards. There are 4 5s out of 52 cards. And again, that because the sample space goes up here. So we go to our calculator here, or no, you don't even have to. You can probably just figure that out here because these are going to cancel. But you're going to be left with 1 over, basically this is like 1/13 times 1/13. The answer is going to be 1 over 169. Now, what happens if you put those back? What's the probability that you get a king and a 5 if you don't replace the cards? Well, that's the probability of getting a king multiplied by the probability of getting a 5 given that you already got a king. Well, what's the probability of getting a king? Well, 4 out of 52. And the probability of getting a 5 now, there are going to be 4 5s in there still, okay, but we took out a card already. Okay, we took out the king, so now there's only 51 cards left over here. So now we've got 4 divided by 51. We're going to multiply those together. And when we simplify that, and I'm just doing this quickly on my calculator over here, I'm going to get 4 over 663. Yeah, it's a much smaller number here. Okay, well, not ridiculously small, but anyway, it's when you compare those here, this is smaller than this one here because of that added restriction. We're not putting the card back. How about one of the cards is a king and the other is a 5? Okay. So that's the probability, this is the probability of getting a king then a 5 or a 5 then a king. Well, or it means addition here. So this is going to be the probability of king, I do it like this, king and 5 plus the probability of 5 and king. Now, if you put the card back, okay, if you put the card back, that's going to be the probability of a king times the probability of a 5 plus the probability of a 5 times the probability of a king. And in this case here, when you put those things, that's going to be 4 out of 52 times 4 out of 52 plus 4 out of 52 times 4 out of 52. Essentially, it's the same thing that we did in that previous question up here. There's just going to be 2 of them. So this will end up being 2 out of 169. Now, what if you do this with replacement? So with replacement, this is going to be, again, the probability of K5 or 5K. This will be the probability of getting a king times the probability of getting a 5 given that you got a king, or it's the probability of getting a 5 times the probability of getting a king given that you got a 5. Ugh, a lot going on there. Okay, but this is how you got to think this one through here. This right here is going to be 4 out of 52, just like we did before, and then this will be 4 out of 51. We've already established what that is. Now over here, the probability of getting a 5 is again 4 out of 52. And then the probability of getting a king, given that you've got a 5, well, there are still 4 kings in the deck. But because I took a card out, there's only 51 remaining. And notice that those are exactly the same. And these are exactly the same as what we just did up here. So now there's just 2 of them. And so the answer here is going to be 8, double that, out of 663. That's the probability without replacement.
An example of dependent events would be drawing a white marble out of a container and then drawing which of the following.
Okay, so let's put this together here. So we're looking for a dependent event. Okay, so an example of a dependent events here. Okay, we draw a white marble out of a container and drawing a black marble out of another container. Okay, so would those have an impact? Would drawing the white marble affect the probability or the sample space for drawing the black marble out of another container? No, that's not it. I'm looking for dependent. Drawing a white marble out of another container. No, as soon as you go to another container, you're dealing with another sample space, and so no, the first event will have no impact. How about another white marble out of the container after replacing the first one? Well, no, if you put the first marble back, you've put the sample space right back where it started. No, that's not dependent. The probability doesn't depend. Now, that means that the answer's got to be D, but let's just look at it. A black marble out of the same container without replacing the first marble. Yes. And now, granted, the number of black marbles didn't change when you took the white one out, but the total number of marbles did change, and so the probability is going to be a little different if you don't put that first marble back. And so, yeah, those are dependent events.
A bag contains 3 yellow, 5 white, and 4 orange golf balls. If 2 balls are randomly selected but not replaced, what is the probability of drawing a white and then a yellow golf ball?
All right, so we're looking for the probability of getting a white and then a yellow. So that'll be the probability of getting a white. Now, we're not replacing those, so the probability of getting a yellow, given that you took a white out already. Well, how many balls we got here? 3, 5 is 8, 4 is 12. Okay, so the probability of getting a white is 5 out of 12. That's fine. Now, we've already pulled that ball out, so that means there's 11 left over. And I'm looking for the probability of getting a yellow. That's going to be 3 out of 11 here. Now, I like doing it like that with the fractions because I can simplify. Notice I've got this 3 over the 12 here. That's going to leave me with a 1 and then a 4. So 5 times 1 is 5. 4 times 11 is 44. Now, I don't see that over here, so I got to go to my calculator and convert that to a fraction, and I get 0.1136. The answer is C. It's going to be 0.11 and so on, but that's the number that I'm looking for.
A bag contains 4 black marbles and 5 red marbles. A marble is selected from the bag, replaced, and then a second marble is selected. Determine the probability that both marbles were black or both marbles were red.
Okay, so the question tells us to determine the probability that both marbles are black or both marbles were red. So what that means is I want black and black or red and red. Okay, so we got a little bit going on here. So we're talking kind of about events that might be mutually exclusive or not here. Now in this case they are mutually exclusive because you can't have a scenario where they're black and red at the same time. So this is going to be the probability of black and black plus the probability of being red and red. Okay, so that's us taking into account the fact that the events described here, these OR events, are going to be mutually exclusive. Now, because we're putting the ball back in, these are going to be independent events, so this will be the probability of B multiplied by the probability of B, or the probability of red multiplied by the probability of red. Okay, now let's go and take a look at this. I've got 4 black and 5 red, so that's going to be 4 over 9 times 4 over 9, okay, plus 5 over 9 times 5 over 9. Now remember that the probabilities look like this because I'm putting the marble back in. Okay, so now what is this? This is going to be 16 out of 81 plus 25 out of 81. So what do we got there? That's going to be 41 out of 81. And when I look at my options, there it is at the bottom there, D.